Okay, today we will do a class review. Actually, we have a very heavy content in this class. Yeah, let's just start. Okay, and actually, this is our course roadmap, and we mainly focus on chapter one, chapter two, chapter three, and chapter four, yeah, and chapter six and eight. Actually, I plan to spend more time to talk about chapter six at least, and maybe a little chapter eight. But since we spend more time on from chapter one to chapter four, so we don't much time on chapter six and chapter eight. But that's fine. Yes, like I said, chapter six and chapter eight is a real world application based on the theory we talk about in from chapter one to chapter four. Yeah, you can see for the chapter one, we mainly focus on the signals and the system. Actually, this is just the beginning. We before this, we we might now know what is a signal, what is a system. But after this, we know what is a signal, what is a system, and how to define it, and how to use a mathematical form to represent it, and some properties, different types for signals and different properties for systems. And the chapter two, we focus on the LIT system. Actually, the LIT system is a special system. Uh, do you know why we focus on the LIT system? Do you know? Yeah, we talk about actually the LIT system has some properties we can use. Yeah, we have already learned that, and those properties can help us to analyze those kind of system, and also many systems in the real app in the real world can be modeled as a LIT system. Yeah, that's the reason why we want to learn LIT system. And after LIT system, we learn the Fourier series and Fourier transform. Actually, we spend a lot of time on Fourier series. Yeah, uh, like and a little time we have spent time on Fourier transform, but now a lot because if you compare Fourier series and Fourier transform, you will see it's very similar. The Fourier series is just specific for periodic signal. The Fourier transform is for all the signal, not only for the non-periodic signal. It's also for the periodic signal. Yeah, and the but and as you know, like after we talk about the Fourier series and the Fourier transform, you will see it's very similar. And for the representation, for the equations, for the properties, yeah. And sampling and communication is just the real world applications. We talk about some. And for the sampling, yeah, you need to know if you want to do the sampling, and for the sampling frequency, you need to choose carefully. Yeah, if you choose it too big, too small, and which means your period is too big, and the after you sample your data, and the sampled data cannot represent the original signal. Yeah, you need to pay attention to that one. Yeah, the communication is just like the signal, the regular signals, like for example, our sound signal. Actually, it's just between in a low frequency. But if we want to transmit it to the other device or some other location, we need to change it to a high frequency signals. Yeah, we talk about it in last class. Yeah, if you forgot it, and just review the last class slides. Okay, let's continue. Actually, we know we talk about in this class we mainly focus on five fundamental questions. Like what are those? Do you remember? Yeah, the first one is how to represent a signal. And do you which chapter help us to represent a signal? Do you remember? Yeah, actually, the chapter one, when we talk about the signals and system, we try to use a mathematical form to represent a signal. Does that make sense to you? Okay, and how to acquire a signal, which means uh, if we want to get a proper signal, how to acquire a signal, which chapter we focus on the how to acquire a signal? Yeah, actually the sampling. Yeah, because you can see if we want to represent analyze a signal, the first thing is we need to acquire a signal. Actually, if you want to use like a computer tool, you want many tools to analyze a signal. Actually, the sampling is the first step. And then how to analyze a signal. Yeah, you can see we learn FS, FT, Fourier series and Fourier transform. It is just two different tools to analyze signal. One is for the periodic, the other for any signal. Yeah, and how to process a signal. Yeah, this is the chapter 2 LIT system focus on. Like it will like how to, yeah, you can see if you have your input and you can get your output. If you your if you your system is a LIT system. Yeah, and the next one is how to transmit a signal. It's just like the communication part. Yeah, in the communication part, we just learn how to transmit a signal. Okay, this is the 5 fundamental questions for this class, and let's try to review how can we resolve those. How can we resolve those 5 fundamental questions in this class? Okay, section 1 we learn signals and systems, and talking about the signals, what you can remember? Yeah, I think I know it's a long time. Uh, do you remember what you can remember? Yeah, actually, we talk about different types of signal. I'm right. The energy signal, the power signal, the period signal. Yeah, and the uh, some non-energy, non-power signal. Yeah. And also we learn some transformations. Yeah, this all the signals can be shift, can be scaling, can be time reversal. But if you know the original one, after shifting, after scaling, after time reversal, the new signal, how can you get that? We talk about that. I'm right. Yeah, for the system, yeah, we just try to talk about some how to represent this signal system. Yeah, we use the differentiation or difference equations to represent a signal. Also, transfer function actually, yeah, and the impulse response. Yeah, we just learn, try to represent the signals using this content. And then we try to learn, we learned some properties for the signals. Memory, if this system is memory or memoryless, is memoryless or not. It is color or non-color. Is stable or not stable. Is TI? What TI? What is TI? Time invariance. I'm right. And linearity. Yeah. And you need to know what are if a system is memory, what does that mean? If a system is carol, what does that mean? Yeah, you need to remember that. Okay, let's talk about let's talk about some details. Yeah, for the signals, we know like we can there are 3 types for signals. The first one is energy signal. What does energy signal mean? Which mean it means the energy is limited. Yeah, and the power signal, what does that mean? Which means the power is limited. Yeah, and the class 3 is otherwise, like the energy is not limited and the power is also not limited, infinite. Yeah. Mm, okay, and we have some like if your signal uh apply like have these conditions, actually you can easily to tell those signal belongs which class. Yeah, for the first class, for the first signal, yeah, a finite signal, no finite length. The finite signal Actually, we talk about what does that mean, which means this signal is finite. The signal's value is finite. Yeah, you can see the value is like smaller than specific value, and the uh, like finite length. What does that mean? Which means the duration time, like the time is limited. It's not like unlimited. Yeah, that makes sense to you? Okay. And then which those signal belongs which class? Do you remember? Yeah, it belongs to class 1. Actually, for the energy signals, and we have the definition, what kind of signal is energy signals. And we talk about the how to calculate the energy, how to calculate the power. We have these equations. Actually, if you calculate the energy for this kind of signal and the power for this kind of signal, you can definitely find these signals just belong to class 1. And then for the class 2, for the signal 2, a periodic and a finite signal, which means this signal is periodic. Let me write down. Periodic and finite signal, which means this signal has the value is limited. It's not infinite. It's not unlimited. Okay, what kind of signal? Yeah, class 2, we talk about that. The other periodic signal is power signal. Okay, the signal 3, like the constant or convergent signal, which means that this signal, the value is equal a specific value, or it will convert to a specific value. Yeah, what type? Yeah, class 2. Yeah, just remember that. And otherwise, if a signal has an infinite length, that the value will go to the infinite, and then it will case 3. Yeah, and then let's talk about how about this one? Yeah, the UN. What's the name for UN? Unit step function, right? What does that mean? Which means n greater or equal than what? Greater or equal than 0. It will be 1. Otherwise, it will be 0, am I right? Which means the n should be should from 0 to the infinite, am I right? So, how about this one? Yeah, actually, it will depends on a. That makes sense to you? Yeah, okay. Actually, um, yeah, actually, we talk about those signals. Actually, these signals, if you want these signals belong to class 1, there should be a condition. It's not like any signals look like that, it will be class 1. Yeah, for the first one, do you remember what's the condition? Yeah, the A should smaller than 1, like the absolute A should be smaller than 1. And for the B, the absolute B should greater than 1. Yeah, how about this one? This one, which means the a should smaller than 0, which means, yeah, because t here it is greater equal than 0, am I right? If you're like a smaller than smaller than 0, which means and you will have the a absolutely t. Yeah, you will have this one, and then it will goes to 0, am I right? So it was class 1. And how about this one? Actually, it's just the opposite. B is greater than 0, am I right? And this one, yeah, this one will P greater than 1 over 2. Yeah, this is just a P series. Yeah, we talk about that. Yeah, okay. And if you see this kind of signals, and but it should have this condition, and then those signals will belong to energy signals. Okay, and then let's try to talk about more examples. And for how about this one? Yeah, the T. Yeah, it's any T, I'm right. So should be class 3. Yeah, because you can see if the T goes to infinite, the value is also goes to infinite. Okay, how about this one? Yeah, actually, this one is just a constant, like no, a constant. It's just a one range. Yeah, it will be class one. Yeah, because it's a finite range, finite let me see. Okay, it is a finite signal, the finite length. Yeah, it will be class one. And how about this one? Yeah, this one will looks like this, and this one, yeah, looks like this. Sorry, this. It will always equal a constant value like that. It will class two. Yeah, how about this one? Yeah, this one actually we talk about that. Am I right? Yeah, it is what equation you can use? Euler equation. Actually, you can use Euler equation to convert it to the sinusoidal signal. Of the sinusoidal signal, we know it is periodic signal. Am I right? So it is class two. And how about this one? Yeah, which means this t should greater or equal than -2. Am I right? And then, which means it will go to the infinite. Doesn't make sense to you. So, which means this one will go to the infinite. It will class three. That makes sense to you. Okay, how about this one? Yeah, this n will go to the infinite. Am I right? So it will be class three. And how about this one? Yeah, actually, this is class two because it's periodic. The one negative one, one negative one, and one negative one. Doesn't make sense to you? Okay. And how about this one? Yeah, here n should greater or equal than 4. Am I right? And since 5 over 3 is greater than 1, which means this value will go to the infinite as a n goes to the infinite. So it is class 3. How about this one? Yeah, here the n should smaller equal than -2 than 2. Am I right? Because this one should greater or equal than 0. So n should smaller equal than 2. Am I right? Since this is greater than 1, and this one will go to the negative infinite, which means it will like 5, 3, absolutely, sorry, absolutely n, am I right? So, which means it will go to 0, am I right? So it was class 1. That makes sense to you? Okay, how about this one? Yeah, notice this one and this one. Yeah, actually, you can also use Euler equations, class 2, am I right? And then let's try to talk about basic signal transformations. Yeah, a general transformation is defined as this one. Actually, you can see this is what? Time shift, am I right? This is scaling, am I right? If alpha smaller than 0, which means it will include some time reversal, am I right? Yeah, so if you know the original signal and then this is a new signal, and if you want to obtain the transformed signal, which means a new signal, what you should do? Do you remember? Yeah, for first step, it's always like have the obtain the time shift. Yeah, firstly delay or advance the signal like this. Yeah, and then yeah, if beta greater than 0, it will be left shift. Yeah, that makes sense to you. Yeah, left because this is greater than 0, which means the value here, the value will become smaller. The t should, if the t want to keep the same thing, uh, sorry, the totally want to keep the same thing, the t should smaller, am I right? So it will be left shift. That makes sense to you. If it's smaller than 1, which means if you want to keep this value same with the original one, which means this one should like greater, yeah, than before. That makes sense to you. So it will be right shift. That makes sense to you. And then perform time scaling or reversal. Yeah, if this one is negative, it will be reversal. Okay, if absolute A greater than 1, which means the signal will shrink because t, since this one should greater than 0, t should smaller than before. Am I right? So it shrank. If alpha absolute smaller than 1, it will be expanded because t will greater than before. I'm right? Yeah, and that makes sense to you. And like a reversal is just like flip based on the what? Do you remember? Yeah, based on the y-axis. Does it make sense to you? Yeah, okay. And let's try to review the periodic CT and DC signals. Yeah, actually, for the signals, we like the periodic signals because periodic signals can have some rules. I'm right. And for the periodic signal, we usually want, for example, our heartbeat signals. It's not a very rigid periodic signal, but usually we just model it as a periodic signal because it will be easier for us to analyze. That makes sense to you? Yeah. And for the periodic signal, there are some like fundamental things you need to know. Yeah. Firstly, for the CT signals, like periodic signals, yeah, we can define it like this. What's the name for this one? Actually, it is computational like equation. I'm right. Actually, why it is like a periodic signal? Because it can we can use the Euler equation to transform it to the sinusoidal signal. I'm right. All the sinusoidal is a periodic signal. That makes sense to you? Yeah. And this is just the dt. Yeah. Here t and n is both are temps, but t here is continuous, and n here is just discrete time, like 1, 2, 3, 4, 5. That makes sense to you? And for the CT signal, do you remember what's the fundamental period? Yeah, actually, yeah, since we have this is a like a signal, am I right? What is omega now? We know it is fundamental frequency, am I right? And for the fundamental period, it should be 2 pi over omega now, am I right? Actually, that makes sense to you? Yeah. And for the non-periodic, it is 2 pi k, divide omega naught. Because, yeah, for the dt signal, yeah, and it should have this key. Yeah, that makes sense to you. Okay, and for the frequency, yeah, it's like a 2 pi over t now. Yeah, based on this equation. And for this one, it should be like a fundamental frequency should omega now divide k like 2 pi over n. Yeah, because you can see why? Why? Because we need to we want the fundamental frequency, which means the frequency should be the smallest one. That makes sense to you? Yeah, so we need to find the key and then get the fundamental frequency. That makes sense to you? Yeah. And then for the frequency and the relationship between frequency and the oscillation, yeah, for the continuously signals, it's easy to get. And the omega, the like fundamental, this is just a frequency. If the frequency increase, the oscillation will be increased. But for the DT signals, it's not like that. It should be highest around 2 pi plus 1, 2k plus 1k pi, and lowest around 2k pi, which means if k is 0, and this is the lowest, am I right? And then 0 and pi, am I right? K equal 1, yeah, k equals 0, this is pi, and then 2 pi, it will the lowest, then 3 pi, am I right? It should be apply these rules, am I right? Yeah, so okay, yeah, there is a question. If you add in two periodic signals, it will lead a paradox. Will lead to a periodic signal? Yeah, actually for the like a continuous signal, it is, because you can see the like a period is also included pi or yeah, but for the um, uh, DT signal, it is now, it be periodic or not periodic. Yeah, you need to check. Okay, and for let's check one examples. Yeah, given e.g. omega k now n, rank the oscillation rate for the following w omega I values from highest to the lowest. Yeah, we know the oscillation rate has this rule. This is sorry, this is 0. I'm right. From 0 to pi to 2 pi to 3 pi. It was from lowest to highest, highest to lowest, lowest to highest. And then let's talk about those four. And we know like the 2k pi is the lowest. Am I right? And 2k plus 1 k pi is the highest. So yeah, this is which means which one is the highest? This one. Am I right? Yeah, because it is like 1k equal 2. Am I right? Which is lowest? This one. Am I right? And then let's compare this one and this one. And this one is like actually it is 2.5 pi. Am I right? That makes sense to you? Yeah, because 5 over 2, 2.5. It is in the middle. Am I right? And this one, it's 4 over, if it's middle, it should be like a 4.5, which means it is smaller than the middle. That makes sense to you? Yeah, which means this one has a longer distance, like compare with this one. Am I right? Yeah, since the highest is here, which means this is should be smaller than this one. That makes sense to you? Yeah, so the highest should be 5 pi, and then uh, 2.5 pi, and then this 4 pi over 9, and then 4 pi. Does it make sense to you? Yeah, just try check the rule. We just talk about that. Okay, and then let's try to review 5 system properties. The memoryless or memory or memoryless. What does that mean? Yeah, which means if your output just depends on the like signals, the present signals. Am I right? Yeah, it will not depend on the previous. It's not depends on the future. Yeah, the causality, which means it will depend on the signals, only depends on the previous and the present signals. That makes sense to you? Yeah. Stability, which means if you have the input is limited, and your output must be limited. If you result output limited, which means your system is stability. And time invariance, which means if you have like a system, like output is yn, and then after you shift, and your output will be shift at also shift. Yeah, which means your like a system is will not change like according to the time. That makes sense to you? And linearity, which means if you have two different signals, if your two different signals input like this, and your output should have the similar relationship. Does it make sense to you? Yeah, this is a linearity. Actually, these properties can help us to analyze the signals. Okay, and let's if you actually the LIT system is very important. So sometimes we want to tell if this system is if it is LIT system. Am I right? So how? Yeah, usually we know. Yeah, if this this function is just about the input. Yeah, and it's not like about the time. It's yeah, it's just about the input, and then this one is a constant coefficient. It's not like the some variable, some like time. It's not time. It's not function. It's just a constant coefficient, and then this one should be one, no scaling factor. Yeah, and then your system should be a LIT system. Yeah. For example, this one, if it is a like a linearity LIT like uh, if it is a LIT like a system. Yeah, actually here the sum. Yeah, actually it's not a function about the input. The input which means oh I have a x, I'm right, and my maybe it is a ax or like a yeah similar like this. It's just like a try to do something in the input. But here the sum, it is not a linear like a linear function. Yeah. So this one is now LTI system. And how about this one? Yeah. This is time. Am I right? So it's not like it's not like actually it's not about the input. What is input? Input is input signal. Am I right? It is xt or xn. Am I right? But here it is time. Am I right? Yeah. So the sum is now something about xt or xn, and n also is just about time. So this one is also now a LTI system. And how about this one? Yeah, this one it is. Yeah, because you can see it's just about like oh sorry. Yeah, it's also now is because this one it should be scaling. It should be one. Am I right? So this is now like LTI system. How about this one? Definitely not, because this one you can see it is just a non-linear like a property. Does it make sense to you? Yeah. So those four are now LIT system. Okay, let's talk about LIT system. When we talk about LIT system, what do we talk about that? What do we learn? Yeah, actually, we we mainly focus on how to use input to represent the output. Am I right? Yeah, and we learn linear convolution, and and also we know we learn the impulse response. What is impulse response? Yeah, before we talk about impulse response, you need to know what is impulse function. Am I right? Impulse response is just like your input is impulse function, and your like output will be impulse response. And if you, based on the linear convolution and the impulse response, we know the analytic analytical approach and graphical approach, like analytic approach, which means we can use convolution integral and convolution sum to represent the output, like the y t equal xt convolution with ht and yn equal like x convolution with hn. Yeah, and then for this one, and for this convolution, for this like property, for this convolution sum or convolution integral, yeah, we have some properties. The shifting property is very important. We usually use it. Yeah, just remember that the shifting property like just happens when you use some convolution thing. Yeah, communication property and distribution property and associated property. And a graphical approach, actually graphical approach, which means you have some two like the xt, am right, signals or xn, and then you have ht, am right, you convolution with each other, which means you can use the graphical method. Like do you remember when we talk about there are some values and we multiple and add them together. Do you remember? This is graphical approach. Yeah, and then for the impulse response, yeah, we talk about actually if we want to decide this LIT system is correct or not correct, stable or not stable, we don't see the input, we don't see the xt or xn, we only see the impulse response. Do you remember? If the impulse response ht or hn, if it has it if it only has this area, it will be horror. Otherwise, it will be non-horror. Do you remember? Yeah, and also you can tell if this LIT system is stable or not stable just based on the impulse response, which means if your impulse response like a integral, it is smaller than infinite, and then it will be stable. Otherwise, it will be not stable. And also the summation for the Hn, if it is smaller than infinite, it will be stable. Do you remember? Yeah, you can review that. And let's review the linear convolution. Yeah, for the linear convolution, we have two different, the dt convolution sum. Yeah, because dt is just an integral. Yeah, non-integral, like a summation. Yeah, and for the case one, which means we have the you have the like signal, input signal, and the impulse response is like very easy, very simple. Like it's just some kind of like impulse function thing, and then you can use some properties, the shifting property, distributive properties, associative properties. Here, I just use I just list shifting property and distributive property, but you can use other associative property and communication property. And for the case two, yeah, which means you have some you need to like convert like your function, yeah, because you can see the convolution sum, which means the basic thing it's just from the infinite positive negative infinite to positive x multiple with h um, like n minus k like that. Yeah. Do you remember? Yeah, and then you can easy to now easy. You can try to convert your equation with this form, and then you can use this equation to calculate it. Yeah, this is case two. And then also you can sometimes you can convert your equation to this form, and then you can use this equation. That makes sense to you? And then for the CT convolution integral, because it is CTM, right? So it's similar. For the case one, it's just some similar equations, and the xt and the ht is a simple like function, and then you can use some properties to get it for the case two. And then you need to, because for the convolution integral you have the integral function, and you try to convert your equation to this form, and then using this equation. That makes sense to you? Yeah. And then let's try to review the chirality and stability of LIT system. For the LIT system, we talk about that. Yeah, if your like impulse response only have this area, which means yeah, which means your system is chiral. Otherwise, it will be non-chiral. And for the stable, and if your like impulse response have this condition, and then your system will be stable. And for the CT, and if you have this condition, and then your system is stable. Otherwise, it will be non-stable. Yeah, and for the DTLIT system, you also can tell if it is stable or not stable, like mm, using this equation. Yeah, if if a absolute A smaller than 1 and absolute B greater than 1, it will be like this one will be stable. If the A is smaller than 1 and B greater than if A is smaller than 0 and B greater than 0, and it will be stable. Otherwise, it will be non-stable. Yeah, we talk about this. And then, yeah, this is for the LIT system. Yeah, actually, you can see it's not too much. Yeah, but you need to understand it. Yeah, for section two, we like focus on the Fourier series. And then for the Fourier series, yeah, we try to like firstly, we just talk about two different equations. One is signal synthesis, and the other is signal analysis. Signal synthesis, which means we just try to represent the original signals in the frequency domain. Yeah, this is kind of the frequency different frequency. I'm right. And this is just the fs coefficient. Yeah, you need to, if you want to represent your signal in frequency, you need to get your like the fs coefficient. And for this one, if you want to get the fs coefficient and also all the like your signals in frequency domain representation, you need to use some properties. Yeah, the first one is symmetric property, and then linearity and time shifting property, and differentiation and integration property, and multiplication. And based on those properties, actually we also need to know two often used FT pairs. Yeah, one is just uh this one. Yeah, this one. Do you remember like the impulse response, impulse function? And the other is just like a square. Yeah, do you remember square function? Yeah, I think we will review it out. Yeah, we also talk about scaling and conjugate properties. Yeah, this is the FS properties we talk about. Yeah, yeah. To those use these properties simplify the computation of FS. But just remember, not only those properties, also to often use the FS pairs. Yeah. And for the FS related problems, actually there are three different types. The first one is given FS coefficient find the signal. Actually, this one will be very now difficult. Yeah, you just try to use system analysis synthesis equations to use this one, and then try to because this part can be converted to the sinusoidal signals using Euler equation. We know that, right? And then yeah, and for the case 2, and given a signal composite of sinusoidal and find a fs coefficient, actually this one is also easy. Yeah, for this one you can use Euler equation to convert it to the exponential equations, and then compare the equation you get and with signal synthesis equation, and then you can use it to get the fs coefficient. And this case 3, actually this one is the most difficult one, and given arbitrary signals and let you to find the fs coefficient. Actually for this one, what you should do, yeah, you should use two often to yeah, firstly you should calculate the like a now signal like separately. Yeah, because it usually you cannot use in this equation to calculate, because usually the uh, key will be under the, yeah, under for example b over a. Yeah, the a should not be 0. I'm right. So you should use this equation to calculate it. But usually we don't use this method. We just use the properties and the two often used FS pairs. Yeah. Okay. Yeah, this is just important FS pairs. Yeah, we talk about. Okay. And if this is your like xt, if your fs coefficient is ak, and then x negative t will this one, and the x conjugate t will the fs coefficient will be this one. And for the real part, and then you can get the fs like this, and for the imaginary part you can get fs like this. And yeah, uh, yeah, if I think this is just the one example. If your signals fs is just this one, and for the real part, like the yeah, for the real part, it's just the uh because this one is just like you can get a 1, and for the imaginary it will be a g. Yeah, and for the real signals, and we know like any real signals can be formed from the even part and odd part. For the even part, and you have this equation, and for the odd part you have this equation. Actually, for the even part you can see it's just a real AK, and for the odd part it's just the imaginary part like AK. That makes sense to you? Okay. And then this is important. Yeah, this is a example. If you're A1, you have this one, yeah, a negative one is equal to this one, and then real part it is 1. Am I right? The imaginary out part is the imaginary part. One is g, the other is negative g. That makes sense to you? Okay. And for the Fourier transform, actually you can see it's very computers usually want to compute the FT of signal, and we will have two different options. One is periodic, the other is non-periodic. For the periodic, firstly we will compute the Fs coefficient firstly, and then we convert the Fs to the FT using this equation. Yeah, actually we calculate this one, and then using this equation to find the FT. And for the non-periodic signals, we just compute the FT by definition. Yeah, this definition. Yeah, that makes sense to you. Okay. Also, yeah, this is the like analysis equation. This is synthesis equation. Okay, and this is just two very often used FT pairs. Yeah, if your signal is like this one and your FT will this one. If your signal is this one and your FT is this one, is your signal is this one and your FT is this one. Okay, and then this is some common FT pairs. If you don't remember how to calculate it, you just review the slides we talked about before. And if your signal is this one and your FT should be 1. And if your signal is 1 and your FT should be like this. Yeah, actually it's kind of pair, it can opposite. Yeah, you can see why this one is 2 pi, because this one is just like a kind of a frequency domain, am I right? So it should be have some frequency thing. Yeah, and then if your signal is like this, and then your FT should be like this, and then your signal is like this, and then your signal is similar like this. Yeah, you can see it's also opposite. Yeah, it this actually this one and this one they don't have any relationship. I just put it here. It's just help us to remember it easily. But yeah, you can put it in your cheat sheet. Yeah, and we know like if your in time domain your signal is periodic, and in Franck's domain it will be discrete, and in like yeah, similar. If you're like in Franck's domain, it is discrete, and then in time domain, it will be periodic. Yeah, yeah, and yeah, it's in time domain it is discrete, and in Franck's domain it is periodic. Actually, it's corresponding. Yeah. Okay, let's try to review more common FT pairs. If your signal is like this and your FT is like this, yeah, we talked about this before. And if your signal is like this and then your FT should like this, yeah, if you draw it, it's just this one and this one. And then this is your like if your signal is like this and then your FT is just like this, yeah, this is your signal and this is like your FT. Yeah, this is just some common FT pairs, because based on these common FT pairs and properties, you can use to get some complicated FT, complicated signals FT. Yeah, and then we talk about some FT properties. Actually, the FT properties is very similar with the FS properties. Yeah, the linearity, yeah, if you have new signals like this and the new FT should like this, and if you have the new signal like this and the FT like this, and if you have the signal like uh, like this is just a frequency like shifting, and then your signal is just FT is like just like this. Yeah, this is just the frequency shift property. Yeah, if you're yeah, because this one is just equal, yeah, which means actually this one is just like yeah, if we have these signals and your FT is just like this, if you have this signal, like your FT is like this. And also the conjugate time reverse properties, if you're if you have this one and yeah, which means if you have ST and your FT is xj omega and then conjugate and the FT should be like this. Yeah, reversal is just like this. Okay, for a real signal, yeah, this one should equal this one because xt equal x conjugate t. Yeah, and yeah, we also call it a conjugate symmetric. Also, for the even part, Yeah. Yeah, because it is a real signal. So, yeah. And the even part should equal this real even. And the odd part should equal the like the imaginary part. For the odd part, the imaginary will equal negative imaginary. Yeah, because it is odd. Okay. And then yeah, for the even, yeah, for the odd. Yeah, that makes sense to you. Okay. And then integration, convolution, yeah, this is integration. If you have a signal xt and the ft is xj omega, and then for this new signal and your ft like this, yeah, and this is just the this is just the ft is xt is ft, yeah, and this part is x is errand of xt, yeah, we talk about that. And the convolution, which means if you do a convolution in the time domain, which means you do a multiplication in the frequency domain. Actually, this one is very important. This one is the basic thing, the theory thing for the filtering. Yeah, high pass filtering, low pass filtering. Yeah, and the multiplication, which means if you do a multiplication in time domain, which means you do a convolution in the frequency domain. Yeah, this is the FT property. And for the sampling and the communication, yeah, actually we talk about the how to do a sampling. Yeah, just multiple the response impulse response, and reconstruction. It's just like try to try to try to how to do that. Yeah, because you can see after your sampling, you just do a frequency replication. Yeah, just a copy, copy, copy. Reconstruction is just try to just find the low frequency part, which means you apply a low pass frequency. Yeah, you can review what we talked about in last class. And also for sampling, the operations change the bandwidth. Yeah. And the communication, yeah, we talk about the modulation and the demodulation. Multiplexing and demultiplexing, we didn't talk about that. Sorry. Yeah. And okay, this is all we talk about that. Yeah, so many things. I'm right. Actually, we haven't talked about the solution to the midterm 3. I don't know if you review it. Yeah, actually, it's the solution, the midterm 3 actually is not that difficult. You can see a CT periodic signals has fundamental T, which means you have the fundamental frequency 2 pi over T, am right? And the non-zero Fs for Xt is just this one, and find the Xt using Fs synthesis equation. Actually, this is synthesis equation, am right? And then for now, you know the A1, A negative 1 conjugate A2, A negative 2. So, which means, firstly, here, the G, you need to using this one to represent it. Yeah, this is the polar representation for G. Yeah, and then you can get this one. Yeah, and this one, this is just A1, A negative 1. Yeah, since it's conjugated, so which means the A negative 1 should be negative E negative G here. I'm right. And then, yeah, many students make this mistake. Okay, and this one is easy. And then you can get this one and step by step. And here is xt real, imaginary, or complex. Actually, you can see for this one, the A key equal A negative key conjugate. Am I right? Yeah, because this one is real, so there is no imaginary part. Of course, A2 equal A negative 2 conjugate. So it is real signal. Am I right? Yeah. So is I see even odd or non-even non-odd. Actually, you can see here, A1 equal negative A negative 1, A2 equal A negative 2. So what does that mean? It's non-even, non-odd. Yeah. Here, find the real part and its Fs coefficient. Actually, we know here, we know the xt is real. Am I right? So which means xt is only have the real part. So which means the bk should equal ak. And the then the fifth will the question 5 will be easy because this signal is real. There is no imaginary part. Yeah, so the CK should always 0. That makes sense to you? Yeah, this is tricky. Yeah, many students just make a mistake. Okay, let's talk about this one. Actually, this one, yeah, you can see we learn how to find the fundamental frequency and fundamental period. Am I right? Firstly, you just talk about fundamental period. Yeah, this one we just ignore that. It's just a constant. And for this one, it is 2 pi over 6. And this is pi over 3. Actually, you can use the K1, T1 equal K2, T2, and then find the K1, K2, and then find the T. But here you can see this one is pi over 6, and this one actually is pi over 6 multiple 2, am I right? So it has a common base. The fundamental period, usually it is the smallest like common atom. So which means the fundamental like frequency should be pi over 6, and then the period should be 2 pi over omega naught. It should be 12. That makes sense to you? Is T even odd or not even not odd? Yeah. Yeah, since this one, you can see this is this one is the even part. This one also even part because you can see this one is to, if you just draw every part, this is even, am I right? And this is this is also even, am I right? This is odd, am I right? So which means this one has even part, also odd part. Yeah, so non-even, non-odd. That makes sense to you? And find the fs coefficient. Actually, you can see, yeah, use the Euler equations to convert this equation to exponential equation, and then you can use to get the fs coefficient and find the even odd part. Yeah, even part, odd part. Yeah, actually, we talk about that. This is even part. This is odd part. Am I right? And find the fs coefficient for the even part and the yeah, and the odd part. Yeah, we know like the uh even part is just like this, the odd part is like this, so which means for the, yeah, this is just the even part, this is just the odd part. Does it make sense to you? Yeah, any question? Yeah, okay. So for the problem 3, yeah, actually this one is, it's not difficult as I know, but some students didn't answer it very well. You can see this one. Yeah, since the A naught equal to, we talk about that. If you want the use the integration properties, this the A naught must be 0, because if it is not 0, and this one should not be periodic, am I right? So there is no fs coefficient because this one is not periodic. That makes sense to you? Yeah, the real part for the xt. Yeah, you can see here. Based on this one, we know like the AK equal a negative K conjugate. Yeah, and then the XT is real. So the CK should equal the AK because this is a real like a signal. And the even part, yeah, we know like the even part is just the real part AK. So which means that this is the real part, this is the real part. Yeah, that makes sense to you? Yeah. Okay. Yeah, just pay attention. Yeah, real signal and the real AK is two different things. Am I right? Yeah, this one. Yeah, we talk about the scaling inter properties. It will not change the like the fs coefficient, but this one it will change AK or like ek a now or e now. Yeah, it will minus 1. Yeah, this is 2 minus 1 is 1. I'm right. And otherwise, it will, like other atoms will not change. That makes sense too. But it will change the period. Yeah, we talk about that. This scaling will not change the AK, but it will change the period. Yeah, and then for this one, yeah, we know from the properties, like in differentiate properties, we have this property and then this one. That makes sense to you? Okay. Okay, and this one, actually this one is, we talk about in the class. Yeah, you can see after derivative, you can get this one. And then we know this one, right? And then this one, you can represent this one using this one, using this equation. And then you can easily to get the CK, and AK is just using this equation to get AK. Yeah. Okay. And for the bonus, yeah, I think this one is also, sorry, it's not that difficult. You can see this one actually, yeah, actually those two we talk about in the class. Yeah. The scaling will not change the AK, only change the period. Yeah, but there is a tricky. Yeah, since here you need to use this one. Yeah, which means this is just a shifting part. Yeah, and then the AK will not change. Yeah. Okay, you can get this one. And then for this one is also now, yeah. Firstly, do a shift, am I right? And then do a reversal. Yeah, that makes sense to you? Okay, this is what for the midterm 3. Yeah, if you have any question, if you have any questions about those problems, just let me know. Okay. This is today's class, and actually we have